So again, these may be slides that Dr. Song showed you last semester, but I think it's important to go through them again a little bit. So what is reservoir engineering? It's a subdiscipline of petroleum engineering that seeks to determine and maximize the ultimate value of hydrocarbon, water, or storage resource. So the other subdisciplines would probably be drilling, production, maybe petrophysics / formation evaluation, and you could argue that there are other subdisciplines as well, but reservoir engineering is certainly a big one. And what our job is to, as it says, determine how much oil and gas is in place, and then to figure out how to get that oil and gas out as quickly as possible and as much of it ultimately out as possible. That's our job, right? And so we classify the reservoirs in a lot of different ways. One of them is the location. So you might hear someone say, well, that's an onshore or offshore reservoir. The mineral type. So this might be, oh, this is a sandstone reservoir or a carbonate reservoir or a fractured or shale reservoir. You might talk about the geology, the type of trap. One thing we're going to talk a lot about in this class is the production phase. So we might say that this reservoir is currently in primary production, in secondary production, or tertiary production. We often refer to tertiary production as enhanced oil recovery. We might talk about the fluid type. So this is something that you would have learned in your fluids class with Dr. Akunu, which is things like, well, is it a black oil reservoir? Is it a wet gas reservoir? Is it a volatile oil reservoir? And then we might also talk about the drive mechanisms, which might be a solution gas drive, a natural water drive, something like that. So maybe a kind of a cartoon of a typical reservoir, a generic reservoir, looks like this. Is that you'll have water, which is the densest of all the phases, is going to be at the bottom. Then you might have an oil column, which is here, which is less dense than the water. And then gas is obviously the least dense, and if you have a gas cap, it'll be at the top. Now, I'd like to point out that you don't have to have all three of these phases, and many times, most of the time, we don't. So you could just have oil and water. You could just have gas and water. You could have no gas or no oil, and you just have water, and we call that a dry hole if you drill that and there's no oil or gas. It's of course important to drill into the layer that you want to produce. So you'd want to drill into the oil column, for example. We refer to the interface between the water and the oil as the water-oil contact line, or WOC. We refer to the interface between the gas cap and the oleic phase as being the gas-oil contact line. Here's another type of geological trap type, but it's the same kind of idea, is that you can have water at the bottom, oil in the middle, and gas at the top, or some mixture of those. One thing, and this is another cartoon of kind of how it looks, but usually you'll have a column of water that connects the surface all the way down to an aquifer. So you may have an aquifer of water that's below the oil layer. You might have an oil layer here, and then you might have a gas cap. Again, you might not have some of those. The pressures of the phases are going to be different. So you'll have, because the density of water is different than the density of oil, is different than the density of gas, you can have different pressures and different slopes of these. This is depth versus pressure along here. The difference in between phase pressures is referred to the capillary pressure. And actually, at the oil-water contact line, this looks like the pressures are equal, but they're not. Maybe you learned in Dr. Sharma's petrophysics class that there is a difference in pressure there, which we call the capillary entry pressure. But what I really want to talk about today and throughout the semester is these different recovery mechanisms. And we often refer to things as primary, secondary, or tertiary recovery. Primary recovery, we can have natural flow. You can also have artificial lift. Some of you might choose to take that class as an elective. We also do special things for unconventional reservoirs like horizontal wells and fracturing, although we do that in more conventional type reservoirs these days as well. But the way the primary recovery works is if here's a reservoir, and this is a little sponge here. And a sponge is a really good analogy for a reservoir because it's porous and it allows for fluids on the inside. It's also
reservoirs these days as well.
And so if we have a reservoir here, then the pressure is going to be quite high. Okay, we're going to be at very deep depths, and at deep depths you have a pressure gradient, so you have a high pressure. It could be several thousand psi. And when we drill a well, if it's a vertical well, it might go like this. What we've since learned is that horizontal wells get more surface area, so you might go in this direction. But either way, when you drill that well, you have that natural pressure in the reservoir which produces fluids. The analogy I like to use is if you take a soft drink and you shake it up and then you open it up, then all of a sudden the fluid comes out quickly. But maybe just a little bit, right? So all of it doesn't come out. Maybe enough to get on your clothes and everything else, but all of it won't come out. We call that primary recovery, when we use the natural flow of the reservoir, the high pressure to produce. And everything about primary recovery, as you learned in Reservoir 1, is really about compressibility. The fluids in the rock are compressible, and it's because of that that we produce fluids. Now, it's odd that, of course gases are compressible, but even oil and water are compressible. As a chemical engineer, I was a chemical engineer a long time ago, I was always taught that liquids are incompressible. And they lied to me. That's not true. Liquids are compressible. They have a small compressibility, but when we're talking about a huge amount of reservoir, that matters. And it's that compressibility of oil and water, in addition to, of course, gas if there's present, is what drives flow during primary recovery. Now, at the end of primary recovery, we might only produce a small amount of oil, maybe 10%. If we're lucky, 20%. For shale reservoirs, it's usually less than that. It's usually more like 5%. So not very much. And what used to happen a very long time ago in conventional reservoirs, maybe over 100 years ago, and what still happens in many unconventional reservoirs, is at the end of primary recovery, you give up. You've produced your 5, 10, 15%, and you give up, and then you go drill another well, or you go to a new reservoir. But what we often do, pretty much with any conventional reservoir, and we're starting to do with unconventional reservoirs, is secondary recovery. Now, what secondary recovery involves is not just a producer well, but then you have a second well. So you got a producer maybe in the center, and then you got what we call an injector well somewhere else. And in the injector well, we inject fluids. Often those fluids are water. I mean, what you want is to inject fluids that are cheap, because you want to inject a cheap fluid and produce your more expensive oil or other hydrocarbon. So a common fluid is water. We call that process water flooding. You can also inject gas. Sometimes it makes sense to inject hydrocarbon gas and displace oil, because oil is worth more money than the hydrocarbon gas. And that could be gas that you produced and then you re-injected. Sometimes you can inject other fluids like carbon dioxide, which I'll talk more about in a minute. That's called secondary recovery. And with secondary recovery, you can get additional flow. Compressibility is not a huge factor in secondary recovery. So as Reservoir 1, compressibility was always really important. Many times we can neglect it in this class because it's really about the water, for example, displacing the oil. So it's a displacement process, and it's about pressure maintenance, as I've shown here. The last technique is called tertiary, or sometimes we call enhanced oil recovery. And in tertiary recovery, we can do things like inject steam or heat. In those cases, if you have very viscous oil like you do in Canada, then by heating up the oil, it reduces the viscosity and makes it easier to flow. In the same way, if you put cooking oil on your fry pan in the morning, it's going to make it less viscous and easier to flow. There are other techniques like solvents. So if you inject CO2 in a supercritical state, almost like a liquid, then that can mix with the oil and make it easier to flow and easier to produce and reduce the interfacial tension. One area that I specialize in is chemical enhanced oil recovery. With that, you can either inject You can either inject things like detergents or soaps. Okay, we call them surfactants, which reduce the interfacial tension and produces more capillary trapped oil. The other is that we can inject things like polymers, which are viscous fluids, almost like hair gel. Okay, so you can think of these things and you inject it, and then it pushes the oil in a much more piston-like displacement. So with tertiary recovery, you can get an additional maybe 10% out. So primary recovery, maybe you get 10%. Secondary recovery, maybe you get another 25%. Tertiary recovery, you get another 10 or 15%, something like that. So if you add up all those numbers, we still leave most of the oil behind, which I find fascinating. We've been doing this for hundreds of years, and every reservoir we've ever drilled, we leave most of the oil behind. And that's why I think it's so exciting to be a reservoir engineer, because there's so much potential. There's so much opportunity for all of us to be heroes for the companies we work for and whatnot, because you're starting at such a low amount. Even after secondary recovery, maybe you only produce a third of the oil. So there's 2/3 there that we can go tackle and try to get out. Here's another plot, and this came from Dr. Larry Lake. And a lot of these slides did in his textbook. I really like it though, so I like to show it. So what I have here is a picture of oil rate, pressure, and oil saturation versus time. And what happens with the pressure, show the second row there, is that we got the reservoir pressure and the well pressure. The well pressure is the kind of the yellow-greenish curve there. And so what happens is that during that time, by the way, I should stop and say that there is if I didn't say it already, there is a way to ask questions. There's a little chat, and if you ask questions there, then I can read those questions and respond to them. So the pressure of both the reservoir and the wellbore drop as we're producing fluids. And it's really this pressure difference between the wellbore and the reservoir. I got my picture right over here. So we got a wellbore, and then you got the average reservoir. It's that pressure difference that drives flow. So fluids flow from high pressure to low pressure. So in this case, if the average reservoir pressure is higher than the well pressure, it's going to produce fluids. As you can see, that these slopes are the same for a period of time. So the difference is the same. And that's why during primary recovery, we might have a period of constant production rate. We'll just say, for example, 1,000 barrels per day. Eventually, the well reaches some limit. It could be 0 psi, it could be a bubble point pressure, it could be something else. But there's some limit where we don't want to or cannot go below. And then we fix the well to a constant bottom hole pressure well. In that case, the bottom hole pressure stays the same, average pressure continues to decline. That means that drawdown pressure, that's the difference between average pressure and wellbore pressure, that drawdown pressure decreases, and therefore production rate declines. So you finished up last semester, I believe, with decline curve analysis. And that's analyzing this decline in this period of constant wellbore pressure. At some point, the production rate gets so low that it's no longer economically feasible to continue to produce. So if you're producing 1 barrel per day, you might spend more money on the pumps and the energy and the technicians to run that, and so that's some sort of economic limit. And at that point, we would either want to give up on the reservoir all itself or to do something different. You can see here that I've indicated that a typical, and I use typical lightly because every reservoir is different, but a typical value is 10% recovery during that period. And then I've also shown the average oil saturation. Now during this time we produce oil and we produce very little water. And so maybe at first glance it seems surprising that the average oil saturation remains approximately constant. The reason for that is that the oil expands. It expands much more than the water does. So it expands and it fills up the space that's being left behind as oil is being produced. So even though the mass of oil is going down, the volume or the percent of the volume remains about the same. It might decrease a little bit. These are just qualitative pictures. But at the end of this period, we'll start on secondary recovery. Secondary recovery could refer to a lot of different things. One of those is water flooding, and it's the most common, so sometimes I'll use those interchangeably, even if I shouldn't. But here I'm talking really about water flooding. So when we do that, we have an injector well, and we're injecting water, and it's higher than the average reservoir pressure, which is higher than the well pressure. So fluid flows from the injector to the reservoir, that's the water, and from the reservoir to the producer, which is mostly oil, at least at the beginning, and I'll talk about that. And so what happens is the oil rate increases and the total rate increases. And what you see at some point is that you have water breakthrough. So the water that you've injected has started to bypass the oil and breaks through and starts getting produced. And so at this point, you're producing both oil and water. So the dashed line is the total rate, oil plus water, and the line here is just the oil rate. So early on, most of what you're producing is oil, but as time goes on, more and more of it is water. And there becomes a time where you're producing so much water relative to oil that maybe it's not worth it. The average oil saturation during secondary recovery does decrease because you're replacing oil with water. And again, compressibility is a small factor during secondary recovery, even though it was a large factor during primary recovery. We will talk most of the semester about secondary recovery. We'll also talk about tertiary or enhanced oil recovery. And a lot of the fundamentals, a lot of the physics, a lot of the equations are related between secondary and tertiary recovery. And so in that case, we inject a new fluid. Could be a surfactant, could be a polymer, could be CO2, could be steam. And in those cases, maybe the pressures remain about the same. We produce more oil and replace it with another fluid, so the oil saturation decreases some more. And we'll get a little bump in oil rate, which will again decline. The total rate it does something a little funny here where it decreases and it increases. That's due to what we call an oil bank, but we'll talk more about that later in the semester. So I really love this slide as an overview, and I credit Dr. Larry Lake who put this together, and I show it every time I teach reservoir engineering or a related class. We will talk about secondary recovery. We're going to talk about one primary recovery method that you most likely, and I'm almost positive you did not learn in Reservoir 1. At least I was never able to get to it, and I think Dr. Song confirmed that she didn't either. And that is natural water drives. Okay, and I like teaching that first in this class because it's a good introduction to artificial water drives or water flooding, which comes next. And then basically the way that this works is you have an oil zone and then you might have an aquifer underneath or surrounding the oil zone. And as the pressure in the reservoir drops, that allows for water to encroach the reservoir from the aquifer. And so you have a water invaded zone and then that pushes the oil out. So it's like having an injector in water in a water flood, except you don't need to drill an injector because it's already there. It's natural, and it naturally invades. And so that's what's called natural water drives. Sometimes these can have high recoveries, maybe higher than what I indicated before.